In this lesson, you'll learn to find the distance between a point and a line and find the distance between parallel lines. How does the distance between parallel lines relate to hanging new shelves? When installing shelf brackets, it is important that the vertical bracing be parallel in order for the shelves to line up. One technique is to install the first brace and then use a carpenter's square to measure and mark two or more points the same distance from the first brace. You can then align the second brace with those marks. In Lesson 3.5, you learned that if two lines are perpendicular to the same line, then they are parallel. The carpenter's square is used to construct a line perpendicular to each pair of shelves. The space between each pair of shelves is measured along the perpendicular segment. This is to ensure that the shelves are parallel. This is an example of using lines and perpendicular segments to determine distance. The shortest segment from a point to a line is a perpendicular segment from the point to the line. The distance from a line to a point not on the line is the length of the segment that is perpendicular to the line from the point. Draw the segment that represents the distance from point A to line BP. Oh, that's a line. That means we could extend it forever in both directions. And we need to extend line BP because to make it perpendicular, it wasn't long enough. And you can compare my freehanded version to the computer drawn one. So the line that we needed there was line AT. Construct a line perpendicular to line S through the point V at 1, 5, not on S. Then find the distance from V to S. Okay, the book shows using a construction tool that is called a compass. I've kind of gone away from that because we know the slope of line S. The slope of line S, it's going down 1 and over 1. So the slope is definitely -1. And we know that to find the slope of the line perpendicular, it's the opposite reciprocal. So we want a line that has a slope of +1. So we want our slope to go up 1 over 1. And if we just use that basic definition of perpendicular lines having opposite reciprocals, we can get a really nice result here. Let's keep going. Doesn't take too much imagination there to see that we're going to cross at -2, 2. And I find that we have better success using the definition of slope than we did with constructions anyway, because people would get off a little bit when they use their pencil, ruler, and compass. We're back again to using the distance formula. Difference in the x's squared plus the difference in the y's squared. So I've got 2 points. I can use the distance formula. The difference in my x's, I'm going to have 1 minus -2, so +2 squared. Difference in the y's, 5 minus 2 squared. So 3 squared plus 3 squared is 9 plus 9, which is the square root of 18, which we could simplify to 3 square root of 2, or as a decimal rounded to the nearest hundredth, it's about 4.24 units. The distance between two parallel lines is the distance between one of the lines and a point on the other line. Recall that the locus is a set of all points that satisfy a given condition. Parallel lines can be described as the locus of points in a plane equidistant, equal distances, from a given line. In a plane, if two lines are equidistant from a third line, then they are parallel to each other. Two lines in a plane are parallel if they are everywhere equidistant. Equidistant means that the distance between the two lines measured along a perpendicular line to the lines is always the same. The distance between parallel lines is the length of the perpendicular segment with endpoints that lie on each of the two lines. The distance between two parallel lines is the distance between one of the lines and any point on the other line. Recall that a locus is a set of all points that satisfy a given condition. Parallel lines can be described as a locus of points in a plane equidistant from a given line. In a plane, if two lines are equidistant from a third line, then the two lines are parallel to each other. Find the distance between the parallel lines A and B, whose equations are y equals 2x plus 3 and y equals 2x minus 3 respectively. The first equation has a y-intercept of 3, and it's going up 2 over 1. The second equation has a y-intercept of negative 3, and it's also going up 2 over 1. Now we can pick any point. They picked the y-intercept of the first line. Why not? Good enough. And then we have to find that point. The line that they drew is perpendicular to the first two, so it's going down 1 over 2. So its slope is negative 1/2, and the y-intercept we said was 3. So the equation of our new line is going to be y equals negative 1/2 x plus 3, and we want to find where that crosses, y equals 2x minus 3. So conveniently they're both solved for y, so since they both equal y, we can set the x parts equal to each other, so 2x minus 3 must equal negative 1/2 x plus 3. Let's add 1/2 x to both sides. So 2.5, usually we want improper fractions, so 5/2 x minus 3 equals 3, and add 3 to both sides. 5/2 x equals 6. We multiply both sides by the reciprocal of 5/2 is 2/5. I get lovely x equals 12/5. I can now take that and substitute it back into my y equals equation to find y. I'm just going to use that one. Negative 1/2 times x is 12/5 plus 3. Cancel. So y equals negative 6/5 plus, I can make the 3 into fifths, be 15/5, so y equals 9/5. Lovely. It might be nicer to have them as decimals. I don't know. Fractions or decimals, it's all the same. Now we need to find the distance between 0, 3 that we had originally and this 2.41.8. So plugging into the distance formula, we have the difference in the x's. So let's go 0 minus 2.4, and the difference in the y's, 3 minus 1.8 squared. So that's going to be negative 2.4, but we don't care because we're squaring it, and 1.2. Using my handy dandy calculator, I get 5.76 plus 1.44, and again using the calculator, the square root of 7.2 is about 2.68, rounding to the nearest hundredths place. The distance between a point and a line is measured by the perpendicular segment from the point to the line.